So the flux density is reduced about 25% for an increase in 3 of the mantle permeability. Okay. So the next problem I want to look at, so we're looking at the DC magnetic field in this problem, and in general the Earth's magnetic field will have some low frequency variations, and this will induce currents to flow in the Earth's crust. So this is a subject of Magnetotellurics here, where we induce current in the Earth's crust, and we're going to look at variations in the Earth's magnetic field of amplitude roughly 1.3 microtesla, and with a period of 100 seconds, so we'll have a frequency of 0.01 hertz. And I'm maintaining this local crust permeability of 1.02. So let's open the QuickField simulation here, and I'll close this model. Okay, so let's look at the geometry here. Now this is an XY symmetry. If we go to problem properties, you can see I've chosen AC magnetics with a frequency of 0.01 hertz, and this is plane parallel. Now if we look at the block labels, this is an air region, and this is the crust. The air has relative permeability of 1. The crust, which has a surface at 0 kilometers, and we extend down to a depth of negative 21 kilometers. In the crust, I'm giving 1.02 permeability and a conductivity of 0.5 s per m over this portion of the crust. The sides of the model, I've given 0 tangential field, and on the top I've chosen a tangential field of 1 amp per meter, and this is roughly going to give us a microtesla field at the Earth's surface. It's varying with a period of 100 hertz, 100 seconds. No vertices are defined in the model, so let's go ahead and solve it. It's already up to date, but I'll solve it again here. And you can see that this is the magnetic field, which if we plot the make a vector plot of the magnetic field, you can see it's the magnetic field's actually attenuating as we're going into the Earth's crust up to a depth of about 21 kilometers for the ultra-low frequency field. Okay. We can also plot, make a contour plot of the current density as a function of depth here, and I'll go ahead and just put in a contour by hand here and look at an XY plot of the total current density, which is roughly 10 to the negative 4 amperes per square meter at the surface, and attenuating as we go into the crust up to, so far the contour went to 21 kilometers into the crust here. Now if we look back at the solution here, it seems like it's a little bit rough. We could refine the solution if we wish, and we can solve and refine. It's suggesting we increase the nodes to 3290, and we can get a little bit finer mesh and a little bit more accuracy here. However, this is perfectly fine. And furthermore, we could actually get the same results by moving the boundary over here. So this slice could be made arbitrarily thin, if you're dealing with node limitation, you can just simply move this in and make it taking advantage of the symmetry of the problem here. Okay. So I'd also like to look at an AC magnetic simulation. This problem is related to electromagnetic well logging, such as used by Schlumberger. And in this simulation, we have a hole that's drilled into the earth, and we have excitation and pickup coils. They're going to probe the surrounding region. That could be clay or shell or salt water type of region. And I've given a table here of some resistivities. Of course, in QuickField, we'll be putting the conductivity 1 over these values here. So this is the average earth resistivity, dry earth, slate, sandstone, wet soil, and seawater. And we would really like to detect, in a shell region, some seawater, and also hydrocarbons. So the motivation here would be to detect hydrocarbons, or regions that may have hydrocarbons. So let's look at the QuickField model here. And I'll close these problems. So this is logging. Okay, let's look at the geometry. And I will zoom to fit. The problem properties. This is AC magnetics, and this is a little bit higher frequency. We're using a megahertz excitation. It's axial symmetric. Let's look at some of the various block labels. This is the air region. This is the hole that's drilled into the earth. And the z-axis is corresponding to the horizontal axis here. And maybe we can zoom in a little bit further to see some greater details. This is the clay region. I've given it a permeability of 1, a conductivity of 0.01 S per M. This is salt water. Permeability of 1, conductivity of 1 S per M. A shell region, permeability of 1, conductivity 0.001 S per M. Now I have a primary coil, which is conducting, permeability of 1, and actually this is the pickup coil. So the primary coil is carrying a current of 1 ampere, and the second primary coil is carrying a current of -1 ampere. Okay, this is kind of idealized. I just give it a pure current here. So here is the second primary coil, and this is the first primary coil. They're counterwound, so there should be 0 pickup. And the pickup coil is located directly between these two. So there should be 0 pickup if we have a homogeneous region. So we'll just be essentially detecting changes here. There's other operation modes where we could look at the absolute value and so forth. Now the boundary of the solution region is given 0 magnetic potential. I don't care what's going on the boundary, and really we'd like to push this as far away from our region of interest as possible. There are no vertices defined in this model. So let's go ahead and solve it. Okay, so we can see the magnetic field of the coil and the pickup due to the excitation coil, and I could refine this solution somewhat. Now what I'd like to do is measure the current flowing in the pickup, and at the same time I would like to translate the coil along the borehole. So in order to do that, I will go to Tools. I'm going to select Parametric Analysis with LabelMover. Okay, I need to choose a base problem. The base problem here is logging. Okay. And I'm going to add values. Okay, this is the quantity that I'm interested in, is the total current flowing in the pickup coil. So let's add this value. Okay, I'm going to close this. Now I'm going to record steps. Okay, and I want to translate the pickup coil and both primary coils, so I will have to hit the control button in order to select all three. So I have all three selected, and I'm going to translate these in increments of 20 centimeters to the right. I'll add a step. So it's behind the second window, so it has translated it once. And I'm going to repeat this step 5 times. Okay, so it's regenerating the model file for each one of these. Okay, let's close this and get results. So we're calculating the total current here at each variation of the coil. Which is started off at 6.5 milliamps, 3.7 milliamps, 2.4 milliamps, 6.6 milliamps, as we're moving into different conducting regions of our borehole, taking some rather large steps. Okay. And I can plot the results. So this would be the variation in the current flowing in the pickup coil as we've scanned across these different regions. I could make finer steps, of course, with greater solution time in order to translate the coil and get a more detailed analysis. Other quantities I could look at with a counterwound configuration like this, say, would be the total magnetic flux that penetrates the plane between these two coils. And of course, different coil configurations are possible and different frequencies. I could also scan for different frequencies, and I can change frequency in LabelMover to get a maximum response for a given coil configuration and design.